So this is his GitHub repository, and you see that he has like LED drivers, PWMs. He has a half-siding board which has occupancy detector and signals. He has 8 servos, coil-based switch machine drivers, half-siding with PWM, mega multifunction. I'm kind of curious, what does that mean? NeoPixel-based stuff. So he has all sorts of different things, and then he has the sketches library here. And if you go into the sketches library, you actually see the source code for all of them. So here is like the so this is an Arduino sketch for 16 LED drivers, and you see like he's including OpenMRNLite. Okay, that's great. Apparently, he's using the 23017 expander, the GPIO expander that I mentioned at the beginning of the thing. And yes, indeed, he has the GPIO abstraction. So he's using the GPIO abstraction to have the 8 A pins and the 8 B pins for on the MCP017. And then what does he do? He has a configuration, but obviously he has a configuration. So we can take a look at his config.h to see what his configuration looks like. And then he has apparently masts and track circuits and various logic devices for these. So this is pretty impressive. At least I'm very impressed with it. And I totally didn't know that this exists. So that's actually pretty amazing. This is the end of my presentation, and now I guess it is your time to start asking questions if you have any.
Right, thank you for that, Basil. Yeah, I was looking at the example you had, which was for the I/O board for the ESP32 within your GitHub, and I must admit I was struggling to work out how things were being done because I was looking for the CDI side of it, but now you've mentioned it's done automatically in the config side of it. So that's something I hope to be able to try eventually to see where we go. Is this one here? Is it? Yeah.
Yeah, I can go through. So this is the config.h from the I/O board in ESP32. And then what we have here, first at the beginning, we have to basically, we just put the definitions that should be visible in the node browser in GMRI. So the name of the board, the software version, the hardware version. And then I'm going to go at the very bottom, this config def. So this config def is going to be what describes the actual XML. So that's the root. That's where the top level of the XML starts. And you see that because it says, hey, this is the main CDI. And then it has a bunch of entries here. So it has the identification segment. That is the standard identification tag that is part of the CDI. And it will automatically put in whatever values you had up there earlier. Then it puts in an ACDI tag because, well, we support the ACDI standard. The ACDI standard is a specific memory space for setting the node username and a node user description. Then it puts in a user info segment, which is part of the standard components of OpenMRN. It basically gives the node name and the node description. It just like puts basically two fields there for node name and node description. And then finally, it actually puts in the real segment, the segment that contains the I/O board's actual settings. So that is basically a reference. So sorry, yeah. Okay, so this is a symbol, and that is a symbol reference, which actually is defined up there. So here it is. It's a CDI group. The CDI group called I/O board segment. It is going to be in the config memory space. So that's the standard one that is used normally, and it starts at byte 128. So when you have segments inside the CDI XML, you always have to place them at absolute locations in memory. It's always 128. It actually is never anything else, because 128 is exactly how long the user info is. Like the 63 bytes node name and 64 bytes node description, this is always sums up to 128. So this always starts at offset 128. The first one, we just ignore that for the moment. Then it basically says we have some consumer configurations and we have some producer configurations, and then we have the Wi-Fi configuration. And all three of these are basically references to other objects. Here you basically say entry, and every single time you say entry, you basically refer to another object. These are actual groups. The Wi-Fi configuration is a group, for example, which is coming from some library. So there is a header file included which defines the Wi-Fi configuration. Let's actually go up a little bit and take a look. Yeah, here we go. So here we have the ESP32 Wi-Fi configuration. So that is the place where this is defined. We can actually go and try to take a look at that. It must be in the source. Okay, this did not work the way I wanted. There we go. Eventually, it's going to recognize that I clicked it. And then hopefully there is a Wi-Fi configuration. Yeah, there is a Wi-Fi configuration. Mike Dunstan is the one who contributed this. And yeah, it starts with a CDI group. So it basically defines a group in your CDI, both in XML as well as in the storage layout. And it says like, well, do you want to enable power saving mode in your Wi-Fi configuration? Yes or no? Minimum 0, maximum 1, default is 0 off, and it has an enable disabled for the map values relations. What kind of connection mode do you want? So all of these are defining uint8. So there's just 1 byte reserved for them in storage. I never have to tell them like where it is in storage, because it's always just basically laid out consecutively. So the layout is done for me by OpenMRN. So what is the connection mode map? So this is going to be between 0 and 3, and connection mode map is somewhere up there. It's like disabled, uplink only, hub only, or hub plus uplink. So these are going to be the options that are available for JMRI. Then there is the hub configuration, which is then again going to be a group that's defined up there. And then for the uplink, we actually have like a standard configuration to configure a TCP socket for connecting to an LCC network. And then he actually put a couple of bytes of reserved space at the end of this configuration. This is actually an extremely clever thing to do, because if you want to add a new feature and you need to add the configuration for the new feature, you need to actually put that somewhere. And if you have some reserved space, then you can always take away 1 byte from the reserved space, and then you'll have like 5 bytes reserved, but then now you have a new configuration option. And you didn't actually have to like completely redo the storage layout. So I recommend people who are doing production devices that they always keep a little bit of space reserved inside their storage layout, so that they have the ability to evolve the product and add new features. So this is roughly how it works, and you basically build up. All of these are a little bit like structs in C or C++, And then in the struct, you basically have all the different entries that they all have a particular type, which then defines how big they are. And then these entries are basically laid out one after the other, just like like a C compiler would do that. The only thing is that this never does alignment. Everything is always tightly packed so that you get maximum use of your space. So this is roughly how it all works. And you can basically define for every single entry, you can define what is the name, and that would be like a C string, or in this particular case, a symbol, which refers to a string there, and the description and all the different properties. You can basically just describe it. You can describe it with simple C++ objects. And of course, what you see here is very rigid, right? So here it says like min. If you would mistype that, and you would, write it with lowercase min, or you miss the I and you just write mn, then your C++ compiler is actually going to say like, hey, you mistyped this. This doesn't work. Which is actually pretty helpful because it ensures that at the end of the day, your XML is going to be correct. So you did not make a typo in the XML. It's also not going to use any spaces anywhere in the XML. So everything is going to be nice and compact, fully unreadable, but it's good enough for the machines. Did this answer your question, Sarbat?
Yes. So on that example for the I/O board, from what I looked at it looked like you had the option you could either have it as a Wi-Fi node or a CAN node. Is that right? Or
that's correct, yes. Yes. So this use CAN or use Wi-Fi, so that in this particular case, that's actually going to come from the INO. So if I go to the IO board.ino, this basically starts with, hey, you have to define whether you're actually using the ESP32 in Wi-Fi mode or wired mode or both. If you're doing both, you actually created a bridge, a Wi-Fi to CAN bridge, which presumably is your intention in that particular case. If you build a device into the layout and you are always wiring it up, then you would usually just like, oops, yeah, I can't edit here. Then you would just comment it out.
yeah, okay.
If you have a purely wireless node, which is perfectly possible with the ESP32, that you're not running any wires at all, then you comment out the CAN bus part, and then you just use Wi-Fi. And you ensure that all of your Wi-Fi devices they are connecting to the same Wi-Fi network. All of those are Wi-Fi secret, password, etc. All of them you can set here in the. This is the sketch file, the INO sketch file.
Obviously, for the CAN bus, I see you it mentions you use the SN65HVD 230 transceivers, which I must admit I've used them. I think it was.
It really doesn't matter. All the CAN transceivers work. All the CAN transceivers are almost always pin compatible, and in just very few extreme examples where you have like a 3 volt versus 5 volt trickiness, you have to be a little bit careful about it. But the fact that there is a CAN transceiver written here, it really doesn't matter because there are 100 CAN transceivers, and at least 85 of those 100 is going to work.
Yeah, because I must admit I found the 230 SN version. That worked nice. Very cheap from AliExpress. Obviously, you have to be aware that it comes with a termination resistor on them. So
yeah,
obviously you have to remove them, which is easy enough to do. I think we covered that already in some of the literature we've done. So
cool, nice.
That's good. So where would you define? Oh, I see. It's already defined there. Is it on pin 4 and 5? Yeah, that's superb.
As the when you've got Wi-Fi and CAN enabled, have you done throughput testing on the Wi-Fi? Do all the packets coming in on CAN go out Wi-Fi and the other way?
So yes, there is actually there is a sketch for that. I call it CAN load test. And you can use this sketch in order to do the throughput testing. So you can load it full, like boggle it down, and this is going to capture, it's going to do something very interesting for you. It's going to capture how much of the CPU is free. And you can actually take a look at this CAN load test. So this is an Arduino sketch. It is using OpenMRNLite, and there is actually a utility library in OpenMRNLite which logs your CPU usage. So you can use that library, and you can look at this sketch and see how you can use that utility function. And there is some sort of timer and blah blah blah. So there are some specific ways how you use it library, and then you will actually get printouts on your serial console of how much free CPU you have left. And then you can start loading your canvas as much as you can, or as much as you dare. And then you can watch your CPU usage. And if your CPU usage is less than 100, you're good.
What about the CAN packets going out Wi-Fi? Can it keep up?
Yeah, I mean, so you can test that as well. I can tell you, if you connect 16 clients, it's not going to keep up. But of
16
course, like,
Wi-Fi client.
Yeah. So that's not going to work. One client in and out, that's almost certainly not going to be a problem. I don't know exactly where the limit is. But you also have to be aware that different ESP32s have different cores. Like, the original is double core. The S3 is also double core, but different megahertz. And then the C3, that is like single core, but it's not a Tensilica core. It's a RISC-V core, but it has like a different megahertz as well. Again, so that is something that you can actually go ahead and just like try.
Yeah, just sort of, a lot of people have commented, well, not a lot, but some people have commented, oh, why are you bothering with CAN? Why don't you just use Wi-Fi and ditch all the wires and stuff like that? No, I don't have any first-hand experience of, doing a whole layout with Wi-Fi, for instance, Wi-Fi to each node device and letting them all.
I can tell you that there are at least two problems with this. One of them is, how do you know that you have all of your devices online? So that is a little bit of a tricky question. If you have wired up stuff using, like Ethernet cables, and those are correctly pushed in and seated, and the clip is in place, that's gonna work. We know that. Wi-Fi, if one device suddenly, like loses the power connection, now what? Now, instead of, like 28 devices, you have 27. Are you going to notice? Or are you actually going to start to run trains, and then at some point it just derails or, crashes and burns or whatever? So that is a reliability question. The second is, I have not seen a microcontroller that would work without a power cable. So you need at least power. You cannot go wireless. There is no way to give power to the microcontroller without running some form of wire to it. And once you actually run some form of wire to it, then, okay, so now do I run like 2 wires, 3, 4, or maybe just this Ethernet cable? Actually, running the Ethernet cable to the device is less difficult than running a 5-volt power supply with 2 wires. Or even worse, a USB plug. Like running a USB plug to 28 different things on your layout is about 100 times harder than daisy chaining with Ethernet cables. Because where do you get those USBs from? Where do you have like, sockets and wall warts like all over your layout? What is the reliability of your wall warts if you are now using 28 of them? Or you do create some sort of bus? How do you create a bus with 5 volts? 5 volts in a way that it doesn't actually have voltage drop across, like the many feet that you may have in your layout. So there are lots of things that meaning you actually, because you folks were at the time there when you were writing the standards, that you had thought about at the time when the standard for LCC was written. And those are actually important things. So for example, you have a power supply, and then one power supply can feed multiple devices. That was something you thought about. And you wrote a specification for that, a specification that, better or worse, you can argue about a lot of different things, but that specification works.
Mm.
Wiring
Yeah, I guess
5 volts to 28 different, ESP32s all around the layout, that sounds like a nightmare.
Yeah, my
case that
my solution to that problem is to use the DCC bus.
Yes, that is definitely something you can do, but then you have the DCC bus, and then you do some sort of rectification, and then you do obviously then you need to have like presumably a switching power supply, which you have to do like a DC-DC switcher, and then from the end of the DC-DC switcher, you then feed your node, and that is going to work. I hope, or probably you hope, that you do this before the short circuit detection, because then it's also not a particularly great experience when you have like a derailment and suddenly your turnout controller is offline now. Plus the ESP32s actually are not that extremely quick to connecting to Wi-Fi. So now your turnout control is offline. Maybe your train just fouled the turnout because it was not set correctly. And now the turnout controller that was supposed to control the turnout is now offline. So now you can't actually like fix the problem. You have to like 050 the train off the track or like push it around by hand. And it's also a little bit of an undesired situation. So yeah, that actually does work. There are difficulties with it. If you are very careful and you are aware of these difficulties and you did your wiring properly, then it's going to be no problem. Of course, by the time you did your wiring properly, you actually have run 2 DCC buses, because you've run one for the actual track and then the actual track, which is after the short circuit detector of the DCC, like a PSX or whatever. And now you have another pair, which is before the short circuit detector. So now you actually did run another pair of wires in order to feed the ESP32s. It's just that you're now taking a DC-DC step-down controller, which actually is a great idea. And by the way, like if you look at this board, which I designed here in the corner, there is literally a DC-DC step-down converter.